Are they? I haven't checked. Good morning, everybody. Let's see here. I have what I call the roll sheet. Basically, your name and a bunch of boxes, right? So all you need to do, you don't need to sign in blood or do anything like that, right? Just a check mark, okay? And fill it out for this week, right? I have a different record, but yeah, just go ahead and fill it out for the last couple days and today. It's divided up into, again, sort of the 8 a.m., what I call section 1, and then the 11 a.m., right? So if you don't see your name up here, go down. If you want to go by like a nickname or a different name or something like that, you're welcome to, edit this over here. Next week, I'm going to do my best to memorize your names, okay? So if you want to give me a heads up on what I should call you, this would be a good place to do it. All it is a check mark, and send it around. And we'll get that done. Oh, and if your name is not on that list, there's a big problem. We need to fix it now, right? So I updated that this morning from the official self-service data, and so make sure your name is on there. What's due Saturday? Homework. You've gotten into Wiley Plus, right? Started looking at the problems, starting the problems, doing the problems. You really need to get through all of those problems today, and by that I mean not finish them, but like look at all of them, attempt all of them, so that you can come get help when? Tomorrow in Graz, my office hour, right? 7 to or about 12 o'clock, right? Get you help logging in, get you help figuring out which package you need, get you help with the physics, right? And unit conversions and all that kind of stuff. And then we'll be well on our way for next Tuesday, right? Where we really kind of pick up the pace quite a bit. All right, want to do trig review, give you a quick way to do trigonometry, and then move into chapter 2 content and get that started, try and get it about halfway, if not a little bit further, into chapter 2. All right, I was watching you guys yesterday, right, doing all the trig stuff and things like that, and you, everybody tends to reach for, what's the mnemonic that you remember in order to remember all the trig functions? SOHCAHTOA. Okay. When I came to Fresno City College, I did not know about this. My students had to teach me about this. I just had to memorize all the trig functions. But what is it supposed to do? Sine is? What the heck does that mean? Cosine is? Yeah, adjacent to what, right? Oh, right. Hypotenuse I've got, right? Hypotenuse is the long side of the triangle. After that, I was lost, right? And then tangent is stupid. All right. So you suffered either through high school or through an entire semester of trigonometry, right, in order to take the prereq for this class. And what I want to do is I want to show you something, okay, that in about 5 minutes, right, is going to solve nearly all of your trigonometry problems. Okay? And you're going to sit there going, oh my gosh, why didn't they just teach me this in trig? I could have saved the whole semester. And you're not wrong. You could have saved the whole thing. I love mathematicians. It's mathematics I don't like. So, trigonometry deals with triangles of all shapes and sizes, but right triangles are the easiest to work with and the ones that we use nearly all the time in physics because any other triangle isn't worth the time. So we have this right triangle. We usually have an angle, right? And we're given the length of the hypotenuse. Okay, I'll just call it simple A, right? Whatever it is. So we go about trying to figure out the relationships. Like if I wanted to find the length of the bottom leg of that triangle, the base leg of that triangle right there, right? There's sort of lots of steps I'd have to do, right? So I'll just call this X, I'll call this Y. So if I want to find X, say, right? I've got this angle, and to find X, do I want to use sine or cosine? Yeah, right there, right there. You're looking at that going, what? What do you mean sine or cosine? There's a relationship. If we know the length of the hypotenuse, right? And we don't know X and we don't know Y, we have to go to SOHCAHTOA to figure it out, right? So Don't concentrate on what I'm about to do. Think about the number of steps that your brain has to go through in order to figure this out. First step, right? What's the relationship between the angle and x? Well, I know that the cosine of theta, right? The cosine of theta is the adjacent side. And what does that mean? Adjacent to what? The angle, right? Okay. So cosine is the adjacent side, which we're calling x, divided by the hypotenuse. Okay. So we had to go to SOHCAHTOA. We had to remember adjacent. We had to remember hypotenuse. Okay, fine. That's like 3 steps right there. And now that I've got this, what do I do to solve for x? So now I gotta do some algebra. So it gets even worse. Not only is it trig, it's algebra, right? And I do some algebra, okay, and I cancel this stuff out, and I find out that x is equal to a cosine theta. And in a similar vein, if I want to find y, I would use sine theta equals y over the, right? And then I'd have to do some algebra, a sine theta. So I took a look at this early on in my college career, and I said, you know what? This takes too much mental effort. Every time I've got to go find the side of the triangle, right? I got to go through all of these hoops in order to get there. And I've got better things to do with my brain cells, like video games and eating and sleeping, right? So is there a shortcut here? Is there a way that I can correctly every time get this with minimal thought? My entire existence in college was trying to make math as fast and painless as possible, right? So I didn't like it. So this is what I came up with, and to my knowledge, nobody else has published this or knows about it. I've asked many mathematicians whether this is valid, and some of them initially would say, well, no, and then they'd think about it, and then they'd silently start crying when they realized I've ruined their entire careers. So let me show you. I call it the touching, not touching rule. Okay? So really, you don't want to do any of that. Okay? Touching, not touching rule. If the side you are looking for is touching the angle, you use cosine. If the side you're looking for does not touch the angle, use sine. And what do I mean by that? If the side I'm looking for, x, touches the angle. So the angle always touching the hypotenuse, right? So you got to be able to identify the longest side of the triangle. Do that and you're home free. Because x, that side, is connected to that angle right there. It touches that angle where the angle is defined. So I know that it's going to be hypotenuse cosine theta. 2 steps. Identify whether it's touching the angle, and when it is, write down the hypotenuse cosine theta. All right, and if the side is not touching the angle, what do you use? Sine. It's the only other one, right? Okay, so do you see there? Let's take a step back here. There's something in psychology called cognitive load. Cognitive load is a measure of how involved your brain needs to be in order to pull off a certain skill or make something happen, okay? In the case of learning to drive a car, okay, a person's brain is just overloaded with information and having to put together skills and operate the car and not run into people and other stuff, right, okay? But as you get more and more familiar with the practice, the cognitive load goes down. And I'm going to venture a guess that some of you drove into school this morning and have no memory of your drive into school this morning. It was completely, the driving reflex was in your hindbrain and didn't even make it to the conscious parts of your brain, right? Okay? So cognitive load is an important idea, and we want to be able to reduce it as much as possible so that you have strength, mental energy for doing more important things. And this is what this does. Touching, not touching reduces the cognitive load of having to figure out triangles. And what's more, it works with any orientation of triangle and any definition of an angle that you might have. For example, here is, well, what's supposed to be the same triangle, but now I'm going to move the angle up here. Let's call it a different thing. Let's call it alpha. Okay? So now I want to find x and I want to find y. So let's try the touching, not touching rule here. Okay? If we're going to find x, we know it's going to be the hypotenuse. And now, is the side x touching the angle alpha? Nope, so we're going to use sine. Now, the side y, is it touching the angle? Yep, so use, and that's it. For those of you that are, your brain is now in freak out mode because you're sitting there going, but Mr. Bando, it's x. Isn't x always cosine? No. X does not mean cosine. Y does not mean sine. You've got to get that out of your brain and out of your reflexes. Sine and cosine depend on where the angle is being defined. And we're going to use angles and triangles all over the place. In fact, you even encountered it yesterday, right? Where we kind of rotate triangles into funny orientations, right? But if you're given an angle, no matter where that angle is in that triangle, okay, and you want the side that's touching the angle, what are you going to use? Cosine. And the side that doesn't touch the angle? Sine. And by that I mean you got to remember to put the hypotenuse in, right? It's always hypotenuse times and then sine or cosine. So that's the touching, not touching rule. And that's like most of the trig that we use in this class. We don't, so if you were tortured with a whole bunch of trig identities, you guys have to suffer through that, right? Okay, we don't need that, right? They're interesting mathematical puzzles. There's about 4 of them that the universe uses on a regular basis, but we're not going to get into that level of physics. Okay? So the trig you need to know is really sine, cosine, and tangent. Unfortunately, I really don't have any good tricks for tangent. Tangent is dumb, and we'll talk about that in a little bit. Okay, right? But yeah, tangent has its own little troubles. Just to round off this kind of idea right here, okay? If you do know the lengths of the sides of the triangle, if you know x and y, how do you find the length of the hypotenuse? Right? We go for old white Greek dudes, right? Pythagorean theorem. Know how to find that, right? Okay. So we can go back and forth and do all that kind of stuff. All right. So everything you need to know about trig for this class in 5 minutes or less. Let's jump into chapter 2. Okay, so I asked you to put eyeballs on either the pre-lecture videos or skim over the chapter and try to get a little bit of background and idea about what's kind of happening in the chapter and that kind of stuff. And so the first part of that chapter is a deep dive into the differences between these terms. And a lot of the struggle that you're going to have in learning physics in this class is going to be some terminology. I mean, the ideas are hard enough already, the concepts are hard enough already, but if you don't have an idea of what these terms mean, you're going to struggle, right? So what I want you to do is turn to your neighbors, right? A neighbor or whatever, and I just want you for the next minute and a half or so, nail down these definitions with each other. What does it mean and how is it different from the other two? Go. All right. You just discovered who around you studied and who didn't. Okay. All right. So one of the superpowers that you have in this class, because you are now a physics student, is that you get to decide where the center of the universe is. You always knew it was you, right? Okay. What do I mean by that? If we're going to measure any kind of displacement, distance, anything, what do we need to know? We need an initial point, right? And what are we usually going to call that location?
Center.
The center, and if we assign a number to the center?
0, 0.
Right? The origin of coordinates? You get to pick. In most instances, you get to pick where the origin of coordinates is. I'm going to pick right there. Janitor just hates me. Okay. So that mark right there, okay, this is 0, 0, right? So if I step 1 meter this way, okay, and then 2 meters this way, what's my displacement?
-2.
Minus
-2.
-1 meter. How far did I travel? I started here, I went 1 meter this way, and then I went 2 meters this way. How far did I go? I traveled a distance of 3 meters, didn't I? Okay. But my displacement, where I am now compared to where I started, is negative. Why negative? Because I'm on the left-hand side of 0, right? Okay. And my position is 1. What's the difference between distance and displacement? One is how far you went. It would be like what your GPS or your phone tells you how far you walked in a day, right? But let's face it, what's your displacement at the end of the day? Assuming, what is it?
0.
It's 0. You left home, you came back to home. Your displacement was 0, but did you travel? Yes, you did. You went a distance. Notice there that there is a difference between displacement and distance. They're not the same thing. And this is kind of the essence of physics, is drilling down into making sure we understand the differences in this terminology. Because both of them are very important and powerful ideas. Okay. So, velocity. What's velocity? Okay, we get real good. It's technical. Displacement over time. Okay? So, it's easier to think of it right now. We'll fix this a little bit later. It's how far you go and how long it took you to do it, right? So if you go 50 miles an hour and you travel for an hour, how far did you go? 50 miles. Okay, right? So you're already doing physics in your head. Good job, right? Velocity is how fast something is going, right? So what then is acceleration?
Change in velocity.
What does that mean? I mean, that's the definition of it, but what does it mean?
Like how much you speed up.
It's speeding up, slowing down, and as we'll learn later, changing direction. And here's one of the big mines in the minefield that all of you are going to step on in various ways. Okay? Because, different analogy for you. This class, physics, is hard for many reasons. One of the reasons it's hard is that you've come to me with your bucket of physics knowledge already full. What do I mean by that? You go to a history class, you go to a literature class, you go maybe to a chemistry or something, right? Math class. You usually are coming into that class with an empty bucket. And you're like, fill my bucket, right? And the teacher will just dump information and skill or whatever on you, right? You're learning something new. The problem with physics is you come to me with a bucket that's already full. And you're like, Mr. Bell, I've never taken physics before. I have no idea what you're talking about. But you've grown up in a world where physics is all around you and physics is happening to you. And so you think you know what things mean. You've experienced mass, you've experienced acceleration, you've experienced speed, you've experienced all these things. And while your experience is totally valid, your understanding of how some of those things work is completely flawed. So your bucket is full of like half clean, half dirty water. And one of the things that I need to do before I can even fill your bucket again is do what? I gotta dump the bucket, right, okay? And so you're gonna feel like that in a lot of our quizzes and things that we do. You're gonna feel kind of hammered. You're like, Mr. Balogh, that was mean, that was tricky, that you tried to fool me. I'm like, yeah, I did. I took advantage of what you thought you knew was right, because I want you to see where it's wrong so you can replace it with good knowledge. And this is one of those places. Velocity and acceleration are very different things. They're related, but they're not the same thing. Velocity is how fast you're going. Acceleration is how much that velocity changes. You're speeding up, you're slowing down, or you're changing direction. Velocity is about motion, what the object is doing. Acceleration is how that motion is going to change. If I am running at 10 miles an hour, what's my acceleration? 0. Why is it 0? I'm not speeding up, I'm not slowing down, I'm not changing direction, right? If I'm running at 10 miles an hour and I hit the door, am I going to accelerate? Yes! What word did you want to use?
Decelerate.
Decelerate. It's not a word. I mean, it is, but it isn't. Because in physics, an acceleration is any change in motion. So can you be accelerating and slowing down? Absolutely. We tend to use the word decelerate to talk about the fact that, we're slowing down. But directions matter. If I'm running this direction, is my velocity positive or negative? Where am I going? Negative direction. If I'm running this way, what's my velocity? Positive or negative? Positive. If I am running in the positive direction and speeding up, what's my acceleration? Positive or negative? Positive, okay. If I'm running in the positive direction and coming to a stop, my acceleration was
Negative.
How do you know? I slowed down. What direction was I going? Positive. And to slow down, I'd have to do the opposite direction, right? So that's the kind of thinking, I know, I see confused looks out there, it's great, okay? When you're reading, was there any hope of you catching any of that idea? Probably not. I'm not saying you're stupid. I'm just saying on a first pass, watching a video, reading the book, you're going to be like, okay, acceleration is this, velocity is this, I got it. And then you're going to come here and I'm going to be like, right? Don't feel bad. You are not stupid. These ideas are hard, but they're important. The distinction between all of these things is vital. So, what we're going to do, okay, to help you see if you know or you don't know what's going on, is we're going to do a quiz. A quiz in my class is an excuse, okay, to find out what you know and what you don't know, right? So what I want you to do is I want everybody to take 3 of these, pass them back. I have no idea if I'm getting out the right number. We'll load balance here. We'll make sure everybody back gets some. Send those back. Like I said, 3 each. These are the sheets you're going to be doing quizzes on. And I'll explain how quizzes work here. And then we'll do a quiz. Take 3. want to end up with 3 of these sheets. Right, where did we run out? We got extra. Cool. Everybody got some? All right. Try to remember to bring these. If you don't, you can do it on a regular piece of paper and just attach it and put it in the pile. You'll be turning these papers in near the end of the semester, so try to keep a hold of them. Try not to lose them. If you lose them, let me know. We can fix it, okay? So make sure to put your name on your quiz sheets. And then these numbers are wrong, but we're doing quiz 2.1 and 2.2. So you want to label these quizzes, right? It's 2.1 and 2.2. Quizzes in my classes almost always come in pairs. And it's not going to be 2 different questions. It's going to be exactly the same question twice. The first time you do the question, you are going to do it by yourself. It's all you. How many times have you been sitting in a class and a teacher asks a question and you're sitting there going, oh, wait a second, I got this. And then the person next to you blurts out the answer. What happens to your train of thought as soon as you hear the answer? It just stops, right? It just derails. And you were robbed of getting some neurons together to form that information in your brain. I don't want that to happen, okay? So I'm going to give you a chance to do it by yourself. Most often you're going to sit there and go, oh my God, I don't know anything, I'm dead. And that's okay, because you're going to do the question again. Only the second time you're going to work with everybody around you. That's why there's 2. But the first time I want you to try it on your own, and you're going to find out what you know and what you don't know. And in the box, I want you to put the answer. And I want a reason for why you're picking that answer. And sometimes students come to me and say, Mr. Balogh, I know that this is the right one and I can't explain why, it just is. I'm like, great, tell me why the others are wrong. Sometimes it's easier to identify the errors, right, than it is to explain why it's correct. So I want the answer and I want some sort of explanation for why you are picking that answer. This is a terrible reason. Just because I said so doesn't make it valid, okay? So you want to be arguing. All right. And then I'll give you a chance, call time, okay? And then I'm going to give you a chance to talk about it with your group. Chances are you're going to want to change your answer. And so if you change your answer, I want you to put the new answer and the updated explanation. Or you can even say, like, not just why you're changing your answer, but why your old one was wrong. I want to see some evidence, right? You've done some analysis. But you do not have to agree with the people around you. This is still your answer. It's just an answer that's now been influenced after you've had an opportunity to teach each other about the stuff that you know and that you don't know. So you don't have to agree, but if you do change it, put the updated. If you don't change your answer, if you want to keep the same answer, then all you need to do is draw an arrow that connects the 2 boxes. That indicates to me you're not changing your answer. You don't have to rewrite everything. That's a waste of time, all that kind of stuff, right? Just draw an arrow down, and that's good enough, okay? After the quiz is over, you are going to grade it. Wait, Mr. Balogh, what did you just say? You just said I got full credit on quizzes? Right? Okay. So the points here, here's the secret. The points don't matter. Okay? To get a full score on quizzes for the semester, you need a total of 50 points. I hand out about 170 to 200 points a semester. When you get to 50, that's it. There's no extra credit. It just stops. Okay? And you've got full credit for quizzes. This usually happens about halfway to 2/3 of the way through the semester. If I'm handing out almost 200 points of quizzes, and I only expect you to get 50, What does that tell you about quizzes? How often am I expecting you to mess up? A lot, right? Okay, again, I'm really pushing on pressure points here in the knowledge that you think you have, or maybe intuitions that you think you have, and you are doing fantastic if you're missing the individual but getting the group one right. And there might be a day where you get both wrong, and that's okay, because there's going to be another day where you're going to get them both right. In the end, it's going to average out. It's not about the points. It's about trying it yourself and then talking to somebody else and teaching each other. How do you know when you know something? You can explain it to somebody else, right? So probably the most important notes for you to get down in your notebook is, I screwed up this idea. I need to look at this in more detail. Or, you know what? I got that quiz. I'm good there. Review this, but you know what? You got it. That kind of note, again, is an actionable item for you to look at when you go to do your study. So here it is. Your first quiz, 2.1 and 2.2. Again, you're going to do it by yourself the first time, and the second time not. Now, if you are welcome in your notes to have a record. Like if you want to work out whatever's going on in your notes, and then just like transcribe the answer and then short explanation under the quiz sheet, that's fine. Because eventually at the end of the semester, I'm going to collect the quiz sheets. You're not going to see them back. Okay? So if you want a record, kind of what you did, feel free in your notes to do that. Okay? But normally these are not recorded. I'm recording this one so everybody can review how the quiz stuff works. But here's the question, and it tends to go by fast. So I'm going to give you like a minute, minute and a half to answer this question. We'll give you 30 more seconds. It's okay if you're stuck. It's okay if you're confused. So about this point, you're going to want to have an answer, A, B, C, or D. And then a reason for why you're picking that. It could be that you drew a picture, right? To try to understand what's going on. Maybe you're describing in words why that one is correct. Or maybe you're describing why the others are wrong. Like how you can eliminate some of these based on what they're telling you. But in some way, shape, or form, I want to see like evidence that you were here, evidence that you were trying, okay? And if you're guessing, just put down, I'm guessing. Right? I don't know what I'm doing here, Mr. Barrow. Right? I'm guessing. That's going to be a record right there. Not for me. I'm not going to ding you for that. I mean, you'll ding yourself. But it's information. You're lost. You need help. Okay? So what I want you to do right now is you're done now. This is set in stone. You're not going to change this answer. I want you to turn to your neighbors, tell them the one you picked and why. Go! reminding you of this later, and hopefully it becomes like natural reflex, but as you're talking, you're gonna wanna be writing down any changes, right? So right now, I let you talk, so if you changed your answer, right, go ahead and put the new answer down and why you changed it, right? But normally, like I'll remind you the first few times, and after that, you'll remember. As you start talking, you'll be like, oh yeah, and then you're right, okay. Take some notes. Just out of curiosity, raise your hand if you changed your answer based on the discussion that you had. No? Nobody changed? Oh, so we're either all right or all wrong. Oh, that's fantastic. I love it. It's delicious. Okay, so how do we know which one's the right answer? You ask me? No, I'm not the source of all wisdom and knowledge. I mean, I've been around the block a lot, but that doesn't make me, I make mistakes too, right? But are there choices up here that we can throw out like right away based on the first sign? A and D, right? What's wrong with A and D? It's got a negative sign for the displacement. And if it's moving in the positive direction, what's its displacement going to be? Positive, right? So A and D are definitely off the table. Okay? All right. That leaves B and C. B and C both have that positive displacement. That's good. So the next thing we're going to check is the velocity direction, right? Okay? So which one of these has the correct velocity if it's moving in the positive direction? C. So is C correct for the acceleration though? We hope so because it's the only thing left, right? Okay. So why would the acceleration be negative if this thing is moving in the positive direction? Because velocity and acceleration are not the same thing, right? They're related to each other, they're both about motion, but you have to think about them kind of independently. Their directions do not have to be the same, right? All right, good job. All right, so if you got both of those correct, 2 out of 2, 4 points, right? If you got, grade yourself. If you got like halfway there, 1 out of 2. If you didn't get it, 0, right? It's okay. You're going to be able to get the point. There was a question back here?
Yeah, a little confused, but I got it correct, but I was a little bit shaky on the velocity.
Good.
What would be a scenario where the velocity is negative?
Moving that way. Right?
Right.
Usually we say to the right is positive. We're going to change that in chapter 4. But okay. And then there's a question up here. Did you have a question?
Yeah, I don't know where to put. So these 2 boxes, or
Yeah.
just
So if you didn't change your answer, just draw an arrow.
Oh.
And then square yourself.
If you're moving that way, then stop the acceleration not positive.
Is the acceleration positive?
Because you're going negative, stopping.
So now we are. So what direction is my velocity?
Negative.
Negative, but I'm slowing down. What direction is my acceleration? Positive, because the velocity was getting smaller. Excellent, I love it. Same question.
Is the relationship between acceleration and velocity inverse?
No,
Because you can accelerate.
What's the example?
because I can be stopped at a stoplight and start moving forward. What direction is my velocity now? Positive, and if I'm speeding up, positive acceleration. You got to look at how the speed is changing. You're getting faster, you're getting slower.
So for velocity, as long as you're going in like positive direction, it's gonna be positive.
Yes,
Okay.
by definition, right? That's the positive direction. That's the direction I'm going.
Okay.
Yeah. So good. You guys, good questions. I love it. How we doing?
Great.
Yeah? Feeling like we can do this physics thing? Okay, let's do something really different. Question.
Just another question regarding the formatting of this.
Hmm.
Am I putting 2.1 and 2.2 as the quiz number for a single box? Or
No, 2 different boxes.
Okay, so where do I put for the second box if my answer didn't really change?
Draw an arrow.
Okay.
Connect the boxes. Okay. I want to teach you really the one thing that you need to know in this class. I mean, that's a loaded statement right there, okay? But if you focus on this, you'll be able to do it all, okay? Now, the details are going to change. You're going to need conceptual background and different things. Physics is hard. We've got lots of ideas. They're all coming together. But if there is one thing really that we are trying to teach you in Physics 2A, It's how to solve problems. Any problem. Anything you come up against. And so how do you solve any problem? In science, you use a method. The scientific method it's not a set of steps, it's an idea about how to approach what we're observing, what we're measuring, and trying to figure it out. And built into that approach is this idea of iteration, where we're going to kind of do the same things over and over and over again, each time trying to weed out the bad to narrow down to the truth. And so if you can grasp onto the idea of problem solving, and one of the worst things you can do in this class is fall into the trap of, well, what equation do I use? You just skipped most of the problem solving, right? And you're going straight to the one thing that you're like, well, I can do math. Did you ever believe that you were going to be in a class where you were grateful to get to the math? That's physics, right? Okay? So, don't shortcut this. Don't shortchange yourself. I know if you're coming up to me and saying, Mr. Balogh, what equation do I use? I now know already you've started in the wrong spot, right? So I'm going to back you up, okay? And we're going to get you going in the right direction. Some books, some websites, some YouTubers, they have I saw one book once that had 18 steps to the problem solving process. I was just like, oh my God, my brain melted. I'm a kind of person, my brain is such that I can't really remember more than 3 things at a time. And so my 4 steps here is kind of pushing it, right? But over the years, I've distilled the problem solving process down into these 4 ideas. Steps, if you will, if you want to think about it that way, but really there's kind of a circle here, okay, that happens. And what I'm giving you, right, okay, so if you're going to build a house, what do you need in order to build a house? You need supply, you need like concrete and wood and nails and all that kind of stuff. So you need stuff. You need a blueprint, which is what? A plan, isn't it? Okay, a plan for what you're going to do, okay? What's the third thing you need? Well, yeah, that's implicit in the supplies. The people to do it, right? Okay? Visualization and strategizing. These are the steps where you are going to form the plan. The plan is not the equations. The plan is how you are. So the other thing you need to build a house is tools, right? So the equations of physics, the kinematic equations that I'm going to show you, those are tools in your toolbox. You don't go to the toolbox and ask a hammer how to build a house. Right? At least I hope none of you do, especially if you're in construction management. The hammer doesn't know. You need the blueprints. You need the materials. So we got to lay out the materials, we got to lay out the blueprints, and then get to the tools, right? Don't think that the equations will lead you along. They won't. Visualization. This is drawing pictures. It's making lists. It's organizing information. It's reading between the lines to see if the problem is inferring or telling you information like an object comes to a stop. What do you now know about that object's final velocity? It's 0, right? So they didn't explicitly say it was 0, they just told you it came to a stop, right? Oh boy, reading comprehension is now a thing, right? Okay, so we visualize, we put ourselves into the situation if we can. Maybe there's an experience that we've had that will help us, right? Understand what's going on here, but you've got to get this big picture before you can go into detail. And then in the strategize step, that's where we're going to start implementing physics and really get a plan going for what we are going to do. This involves looking at the toolbox and going, well, what tool is appropriate for this? And then what do you think the do it step is? You actually do the strategy that you've come up with, okay? And then the check it step is what? Find out if what you got makes sense. There's lots of different ways to do that, okay? So, I want to model the problem-solving process for you, okay? And I'm going to do it with something called one-dimensional horizontal motion. And to do that, I need to give you the toolbox, okay? And I'm gonna write it in two places. I'm gonna write it on the iPad, but then the iPad screen's gonna go away. So I'm gonna write it on the board because we're gonna need to refer to it a lot, okay? And now I'm giving you these equations in a vacuum. You don't know where they're coming from. I'm literally just kind of handing you the hammer, the screwdriver, right? And the pliers. And then I'm gonna show you how to use them, okay? So, there's one of them. There's another. And there is a third. Okay, I'm gonna write them up here on the board and I'm gonna keep talking. What just happened?
Got some tools.
Your brain probably shut off. I'm guessing. You've been trained over the years that as soon as math appears on the board or the screen, that you are in for an hour of pain. Or boredom, or something. And so your brain's reflex was to go, okay, math. Maybe a good math teacher's in high school or college, I don't know, right? But for me, this was always the gateway to pain. Okay? Math is something we use in here. It's not really something we do. And I know that sounds weird. But just like a French literature major needs to know French in order to really be effective in their major, right? Do they have to know perfectly the grammar and be at the forefront of French language? No, right? You need to be conversant. You need to be fluent. But that doesn't mean you need to be perfect. The same thing goes in here. Okay? Math is our language. And it's a language of relationship. It's actually a language of compression and decompression. Compression, decompression is all around you. Anytime you interact with anything on the internet, you are doing compression and decompression algorithms. The video that you're watching on YouTube, okay, is a pretty big file. But to send it to you, they'll compress it down so it can get to you quickly. And when it gets to your device, they'll decompress it so that it looks nice and clean. You will have probably experienced when the decompression algorithm is not working or the bandwidth is limited. The video gets all blocky, right? That's because the compression is too much, right? And visually you're starting to see artifacts. Mathematics is like that. It compresses ideas down into little tiny symbols and shows the relationships between those symbols. So the symbol V, what does the symbol V mean? It's a velocity, okay? But it's different from this symbol that has a little subscript 0 in it. Do you see that? Now, when we speak this, we say V, and then we say V naught. N-A-U-G-H-T is an old-fashioned word, naught, and it means 0. So I'm guessing many of you were born between 2000 and 2009, okay? So if I was born in the 1990s, I was, and I'm older, okay? You would say I'm a child of the 90s, right? If I was born in the 80s, I'm a child of the 80s. If I was born in 2013, you'd say I'm a child of the teens. But what if you're born between 2000 and 2009? What do you call those people? Naughties. You're naughty. I love that, okay? All right, so what's the difference? Well, this one V naught, this one's V, but in terms of the idea, this is the final speed something has. This is the initial speed it has. This symbology, V naught, means speed that it starts with. Different from speed that it ends with. What's A?
Acceleration.
Acceleration. What's T? Time. So what this says is, the speed something will have happens or comes about because of the speed it started with and how much the speed changes in time. That was a big long sentence, wasn't it? But notice how we can compress that entire idea down into a single relationship, a single equation. Delta x is a displacement, a change in position. What's V naught? It's the initial, it's what it starts with, right? Okay, what's t? Time, what's a? Okay, so on and so forth. So I know something is going to go somewhere if it has initial speed and time goes by, right? And what's more, if the speed changes, I can get the extra bit of distance that it goes. And then this last one just has more relationship. Now, these tools, so your book, all books, YouTube videos, they all do this wrong, have like 8 of these equations in the chapter. Okay? Maybe even some of them have like minus signs and stuff in them. That is like 5 too many. Okay, remember I told you? I can hold on to 3 things, right? These 3 equations will solve every single problem in chapter 2. You don't need all of those others. There's a 4th one that sometimes comes in handy, but these 3 are really all that you need. And that's why I call them the 3 kinematic equations, 1, 2, and 3. Let's take a look at what's missing in each of these. What does the first one not have in it that the other 2 have? The displacement, delta x, right? So if you don't know what delta x is this tool a good choice? No. If you want to screw in a screw, do you grab a hammer? No, okay? What does this one not have in it? Which velocity? The final velocity, right? It doesn't have a v. It's got a v naught, but it doesn't have a v. And so if you don't know what that is and you don't care, this is good choice, right? What about this one? It doesn't have time, right? If you're looking for time, is this a good choice? Probably not, right? So you want to use the tools where they are strong. All right, so let's do an example of solving a problem and using the problem-solving method. Now, I wouldn't be surprised if you guys could maybe do this one on your own. Like you can, I just sent you to it and you just go, right? And yes, it is a simpler type of problem, but I chose a simple problem because I really want to focus on the problem-solving method. Not necessarily the physics of the problem, but the method we are going to go through in order to tackle this problem. So, the first step in the problem-solving method is visualization. Again, try not to focus. All of your eyes just turn and you're reading the problem and like, I gotta understand it, right? Be here. Be present with the problem-solving method. Not this problem, but the method I'm trying to teach you. Don't worry about the details. It's all going to be on the PDFs and the YouTubes and all that kind of stuff if you want to see it later. But we're concentrating on the problem-solving method. So, a visualization. Again, it can be a picture. It can be you sitting there, sort of trying to be the person in the problem, right? So we're driving our car along, and we're coming to a stop. You've experienced that, right? Coming to a stop in front of a stoplight. So we can draw a picture. Now, I'm not good at drawing pictures. I'm kind of visually oriented, but sometimes picture just isn't going to get it for me. And one of the things I've noticed that's particular to kinematics problems, so problems where acceleration is constant, is that a list of what I know and what I don't know becomes really, really helpful. So feel free to draw pictures. As a matter of fact, probably on Tuesday I'll have an example where I draw a picture and that kind of stuff. But really, making lists of everything we can know and not know. We know that this toolbox does limit us, right? We can only do work with the tools that we have. And so there is a list that comes out of this toolbox. No, come back. There's a list that comes out of this toolbox that I can make of everything I could know and not know. Where did I get those from? I just went down the equations, right? Could I know or not know the final speed? Could I know or not know the initial speed? The acceleration? the time, the displacement. Okay, so we're back. Do we already have this in our list? All done. All done. Done, right? Okay. So I've identified, right, the boundary conditions, the limitations of my toolbox and what I could know or not know. And so now I want to kind of start reading the problem and start pulling out, do I know this information? I'm going to ask myself, do I know how fast the car is going at the end of its motion? Is there anything in the problem that's giving me a hint? Comes to a stop. So what does that mean? Zero. So I know that my final speed is going to be 0. I'll go ahead and write that one down, and we're going to do this in meters per second. Okay. Does the problem tell me anything about how fast the car is going initially? Yes, it does. How fast is it going initially? 27. And, okay, we'll draw a little picture. Here's my car, and it's going this way, right? And it's going 27, and then ... it comes to 0, right? Okay, so that's a picture you could draw, right? So what direction is the car going? Positive. It doesn't really say, but I can choose, right? So I'm going to say it's going in the positive direction. So I'm going to say positive 27 meters per second. The directions are important. We'll find out a little bit later. Okay, does the problem tell me anything about the acceleration, how fast the car is speeding up or slowing down? We do know it's slowing down, right? But do we know what the value is? Well, 60 miles per hour isn't an acceleration, right? Velocity, and I skipped over it, but you really want to look at units of things, right? Velocity is distance divided by time, and acceleration is distance divided by time squared. Right? So mile per hour is a distance divided by time. So that's a velocity. Okay, so they're not telling me anything about the acceleration, but what are they asking me to find in part A? What the acceleration is. So I don't know what it is, but I'm being asked to find it. So what I like to do is I like to circle, right? Like I put the question mark down because that means I look through and I tried to see if there was anything in the problem that they were telling me, and I couldn't find anything, so question mark. Don't leave it blank, because blank means you didn't do anything, right? Question mark means I'm not sure, or I'm not given it, or anything like that, right? And then I circle what I'm looking for. This is all still visualization. We are organizing information. We're trying to get a handle on what we have and where we want to go. Do we know anything about time? How long does it take for this thing to slow down?
3.1 seconds.
3.1 seconds. Do we know how far the car went as it was slowing down? It doesn't, 60 miles per hour again is a velocity. It's not a distance. Yeah.
So you said displacement earlier. Is that the same as delta x?
Yeah. All right. So here's my list of what I know and what I don't know. I'm after the thing in green. So now I want to come up with a plan. How am I going to get the acceleration, the thing I've circled, if all I know is V, V naught, and T? Is there a tool in my toolbox that would be good to pick? Don't answer out loud. Don't answer it to yourself. I'm looking for a tool in my toolbox that has V, V naught, A, and T, but not delta X. And why do I not want to pick delta X? Answer that. Because I don't have it. I don't know it. It's going to be a problem if I try to include it. Okay? So now answer out loud, which of these am I going to pick? First one. Okay. So what is the plan? The plan is I'm going to use the first kinematic equation and solve it for A. How much math have I done so far? None. But I visualized and now I have a strategy, a plan. That's where this class lives and breathes. That is physics. I beg of you to not skip these steps. At first, it's going to feel like it's a little bit in the way. I can go really much faster, Mr. Bell, if I just guess. But as you get used to this, you are going to save so much time flailing around and not knowing what to do. If you visualize and strategize. Please, write down your plans. Why would you want to write down use first kinematic equation and solve for A? Why would you want to write that down?
In case you get distracted by something else halfway through and you come back there and all what's going on.
You're gonna get so deep into a mathematical jungle that you're gonna need a GPS, right? You're gonna need something to guide you. And the thing that's gonna guide you is, what am I doing? Wait, what am I solving for? And if you wrote it down, away you go. 3 days from now when you're coming back to study what you did, how are you gonna know what you did? It's just a bunch of math. You're going to spend some cognitive load trying to figure out what you were doing back then. But if you wrote a note to yourself that says, this is what I'm trying, you're going to be much faster, more effective. Will I ever grade you down if I don't see you writing down your plan? No. This is for you, okay? I know physics forward, backwards, upside down. I can kind of figure out what you know and what you don't know just by looking at your work. So I don't require you to do any particular method for this class. I'm just trying to convey to you that I know the way to safety, right? And safety and being able to troubleshoot and see what you're doing and all that kind of stuff just makes it so much easier when you go back. Okay, so now that we have visualized and organized the information and we've developed a strategy, we don't even know if it's a good one yet or not, what do we do now? Visualize, strategize, do it. Now we do math. This is where the math happens, right? So I copy down my tool correct. This is one of my big problems. Copy it down correctly, okay? And now do some algebra. You're welcome to put in numbers at this point if you want. I really don't care. I do it symbolically. So I'm going to subtract V naught from both sides, and then I'm going to divide both sides by T. I do math really fast in here because, number one, it's uninteresting. Number two, this isn't a math class. I want to spend most of our time in that strategize, or visualize, strategize, and check it step. That's really where all the physics happens. Most of your grading is going to be based on whether or not I can tell if you can do physics, which is visualize and strategize and check it. I tend to be very forgiving of math mistakes. So if I can see that you set everything up correctly, and then you just made a math error somewhere in your do it, okay? Generally, I might look the other way on that exam. So you know what? They know the physics. They just made a little math error. It's fine.
So if it doesn't say what decimal place in it, it should be
Okay, all right. Significant digits. I didn't want to have to talk about this. I don't care that much about significant digits. I mean, if you've got 15 digits in your answer, I'm going to ask you why, right? Okay, but this problem's got what, 2 sig figs in it? If you were to answer in 3, I'd be like, fine, I don't care. Okay. Always carry an extra sig fig in your intermediate calculations so that you can avoid something called round off error. But it's not a terribly big deal for me. I don't like numbers. Numbers don't like me. That's why I'm not an engineer. Okay, but I'll kind of call you on. If you come up to me with a lab and you've got 20 digits that your calculator told you, I'll be like, those digits don't exist. What are you doing? All right, so now I can drop some numbers in. What's the, okay, 0 minus 27 over 3.1. Then you have a calculator. Did I write this one down? Oh, I did write this one down. Okay, first of all, the number comes out what? Negative. Okay, and the number actually turns out to be 8.7. But what units is it going to have? You can do this one of two ways. You can either put the units into the problem as you go. Like 27 meters per second divided by a second. Okay? I tend to not do that, mostly because I'm lazy and sloppy. And units visually confuse me when I'm doing calculations. If you are using the standard metric units for all of these values, meters per second for velocity, time in seconds, you are guaranteed to get the correct units for acceleration if that's what you're solving for. These tools are calibrated and primed and designed to be something that's called dimensional consistency. This thing is a meter per second equals a meter per second plus a meter per second. And so if you use the standard units, you'll be fine. However, if you did this in kilometers per hour and the time in seconds, now you're in trouble. Those units don't match because kilometers per hour is not the base standard unit in the metric system. Okay? So you would have to convert kilometers per hour into meters per second to be guaranteed to get the correct units out. So I'd say this is garbage in equals garbage out, right? If you're just using whatever units you've been given, you're probably going to get it wrong. If you go back to the standard units, meters for distance, meters per second for velocity, meters per second squared for acceleration, and seconds for time. So if they give you that it travels for 60 minutes, what are you going to do with those minutes? You convert them to seconds so that you're guaranteed to get the correct units out on your answer. So this is going to be a meter per second squared. All right. One of the things I'll ask you to do to help me in grading on exams is I'll ask you to box your answers just so I know which number on the page is the one that you finally decided to come up with. Okay? But we're not done. What's the fourth step?
Check it.
Check it. All right. How do you check things?
Go backwards.
Oh, go backwards. That's one of my favorites. I don't know about you, but I can make mistakes forwards and backwards. In my mathematical career, I've done something wrong forwards and got a number and then sort of like reversed it, like plug it back into something else and made the mistake in reverse and thought that I was right. It was an amazing achievement. I should have kept that paper, right? So plugging it back into something isn't always the answer, okay? If there is another way to get at the value, it might be worth trying. In this case, there really isn't another way. There is a part B of the problem. One of the ways that you, unfortunately, are going to be checking a lot of your answers is by doing what? Like if this is a homework problem on Wiley Plus, what are you going to do? You're going to type it into the box. And if it goes green, you're going to go, ah! And if it goes red, ooh. And that'll be like your check. But a lot of times the universe doesn't have a checkbox, right? So sometimes you got to fall back on your physics knowledge and conceive of what's going on here. We got a number that's pretty close to 10. So this is a trick we physicists use all the time. It's called order of magnitude calculation. 8.7 is really close to 10, right? And 27 is really close to 30, isn't it? And 3.1 is really close to 3. So if we just kind of round the values a little bit, we think about it. I'm going about 30 meters per second right here, right? And 3 seconds later, I'm going to be going 0. So if I start at 30 and over 3 time periods get to 0, how fast am I going after the first 1/3 of the time? 20, right? I go from 30 to 20, and then 20 to 10, and then 10 to 0. How much did my velocity change in each one of those time periods? About 10, right? It went from 30 to 20, that's negative 10. And then from 20 to 10, that's again another negative 10 change, isn't it? And then from 10 to 0. Does that make sense?
Yeah.
Like, is that what I got? Negative, slowing down, that's good, always check the sign. and then I got something that's around 10 after I rounded my numbers. You can't always do something like that, an order of magnitude calculation where you kind of round everything off and see if it works, right? But I'm feeling pretty confident. If I had kind of done that and my answer was like negative 8,000, then I might know, oh gosh, something might be wrong here, right? It needs to be in the neighborhood of 10. Okay, so that's one way to check it. Other ways to check it would be to use different tools if possible. But now, part B asks me, how far does the car travel during this time? So now we have part B is a different problem, isn't it? What are they asking us to find? Displacement. How far did it go? All right. My list is still the same. I still know, as a matter of fact, now I know that the acceleration is negative 8.7 meters per second squared, right? Okay. So, what tool can I use if I want to know delta x and I know everything else? Second one, do I know my initial speed? Do I know t? Do I know a? Do I know a half? Could I use the third one? Sure, I know all of this stuff, but the second one, I don't have to do any math, right? Because the second one's already solved for me. It's delta x equals all this stuff. So my plan is, use the second equation. I would have written this down. I'm not writing it down because my handwriting's sloppy and I'm running out of time. V naught t plus 1/2 a t squared. We're going to use the second equation, solve it for x, already done, and put stuff in. 27 times 3.1 plus 1/2 times negative 8.7 times 3.1 squared. And then I'm going to hope and pray that my TA calculator gets this all right. When I do that, I get 41.9 meters. Now this one's a little bit harder to check through intuition because displacement and acceleration and velocity is related quadratically or by powers of 2. And so, but you can sort of argue, if a car's going 60 miles an hour, do you think it might take the distance of like say half a football field? 42 meters is about 50 meters, which is roughly 50 yards, right? Can you imagine that it would take about half the length of the football field for a car to come to a stop? Sure. If that was 3 football fields long, or just the length of the end zone, it might be, that doesn't sound right. But we actually just gave away the best check you could do to see if all of these answers are correct. What would be a better check? Use the third one, right? If you put your values in for acceleration and delta x and say get the correct initial velocity or something, right? What do you now know? All the values are consistent, right? So sometimes using the tool that you didn't use is a really, really good check. See if you got it right. I hope to see you tomorrow in grass, okay? If I don't, good luck on the first part of chapter 1 homework, right? Get that all done and turned in or finished by Saturday. And I will see you next Tuesday when we will finish up chapter 2.
Room one more time.
What's that? It's from 7 a.m. to 1 p.m. 7 a.m. to 1 p.m. 2:30.
Where is that in reference to office 37?
2:30 is the room that's right, not this chemistry room, but the corner room.
Is there grass for days? Not grass for like physics.